Hello everyone, I'm Likhitha Mankali, a PhD candidate at New York University, working under the supervision of Professor Ozgur Sinanoglu. Today I will be presenting on our upcoming work, Insight, attacking industry-adopted learning-resilient logic locking techniques using explainable graph neural network. This is a joint work between New York University and University of Delaware. Semiconductors are used in different aspects of our lives. Following is a generic overview of the abstraction layer of the chips. For a given chip, attacks could be launched via any abstraction layer. Software bugs can be patched using updates. What if the hardware is compromised? It is challenging to patch the hardware, unlike software. Thus, it is essential to protect the hardware against such attacks. Now let's discuss about the globalized IC supply chain. Before 1980s, the IC design companies followed a vertical integration approach where the design, fabrication, and testing were all done in-house. However, with the increasing complexity of ICs, as shown here, where the latest Apple M1 Ultra has 114 billion transistors, has made owning of fabs prohibitively expensive, as shown in the news article over here. For instance, TSMC has invested $20 billion in building a 3-nanometer fab. In addition, thus, the IC design companies have adopted a globalized IC supply chain where the fabrication and testing of the chip are outsourced to third-party facilities. The involvement of third-party facilities has led to different hardware security risks such as hardware trojans, IC counterfeiting, reverse engineering, and hardware IP piracy. In this work, we focus on hardware IP piracy. Hardware IP piracy is one of the major threats where the untrusted entities in the IC supply chain with access to design of the chip may overbuild or pirate the chips. Are these threats real? Yes. As per a report by US Department of Justice, a prominent IC design company has suffered a loss of $8.75 billion due to IP theft. There are different IP protection techniques proposed in the literature such as logic locking, IC camouflaging, and split manufacturing. In this work, we focus on logic locking that has gained traction from both government and commercial entities. For instance, DARPA has invested in the development of logic locking techniques through programs such as ACE, Eclipse, and Sahara. Similarly, commercial companies such as Synopsys and Mentor Graphics have integrated logic locking to their EDA tools. Now let's discuss about logic locking. Logic locking modifies the original design by adding key gates and key inputs, and the secret key is stored in a tamper-proof memory. Only with the correct key value, the logic lock design functions correctly. Consider an example over here with original design and logic lock design as follows. The logic lock design works functionally correct with an insertion of correct secret key. With an incorrect secret key, the output is incorrect. Now let us discuss about the threat model considered in this work. The design of the chip is done in-house and logic locking is performed on the original design upon logic synthesis. The locked design undergoes physical design and then is sent to a third-party foundry for fabrication. Upon fabrication, the IC is sent for testing and packaging and written back to design house for activation. Now let us discuss about the threat model considered in our work. The design of the chip is done in-house and logic locking is performed on the original design upon logic synthesis. The locked design undergoes physical design and is sent to a third-party foundry for fabrication. Upon fabrication, the IC is tested and packaged and sent to a design house for activation, where the correct secret key is inserted to unlock the design. In this work, we consider the attacker to be located in the foundry. The attacker can analyze the reverse engineered locked design, and the attacker's objective is to retrieve the secret key and pirate or overproduce the chips, thus leading to hardware IP piracy. Researchers proposed various logic locking techniques. There has been a rise of ML-based attacks with the rise of machine learning. Thus, researchers have proposed learning resilient logic locking techniques that protects designs against ML-based attacks that leverage structural hints from the design. In traditional logic locking, the possible key gates are XOR key gate with a key value of 0 and XNOR key gate with a key value of 1, as shown over here, where there is a correlation between the key gate and key value. Learning resilient logic locking techniques remove this correlation between key gate and key values by redacting the inverters as shown over here, where an XOR gate with a key value of 1 and an XNOR gate with a key value of 0 are possible due to inverter redaction. Similarly, the correlation between key gate and key values is removed from mux-based key gates as shown over here. In this work, we target 7 learning resilient locking techniques that includes TRLL and TRLL plus that are adopted by the industry. Existing ML-based attacks such as SAIL, Snapshot, Scope, OMLA and MuxLink fail to attack learning resilient logic locking techniques. Now let's discuss about the preliminary problem modeling of Insight, which is similar to existing attacks. We map the key prediction problem to a GNN-based node classification. We utilize GNN as the circuits can be naturally represented as graphs, and GNNs are best suitable neural networks for graphs. The log design is first converted to a graph, and then we extract subgraphs around the key gate. Then we extract the features of the nodes in the subgraph and send it to GNN for the prediction of key value. We observe that the key prediction accuracy of preliminary problem modeling is around 50%, which is nearly a random guess. Now, how do we find the reasons behind the failure of GNN in key prediction? To that end, we employ Explainable ML to find the reasons behind the failure of the GNN. Traditional neural networks work like a black box and do not provide reasons behind the complex computations. It is challenging for humans to interpret the reasons behind this complex computation as neural networks outputs only accuracy or its predictions. Explainable ML provides reasons behind these predictions. For instance, Explainable GNN provides important features and nodes as reasons behind their prediction. Thus, we employ Explainable GNN in our work to obtain the reasons behind the prediction of the attack. Here is a high-level overview of Insight, where for a given log design, we employ Explainable GNN guided framework to recover the secret key. Explainable GNN provides important scores for features and nodes as shown over here. Now, how do we select a suitable explainer that provides relevant explanations? We perform ablation study on state-of-the-art explainable graph neural networks such as GNN Explainer, SubGraphX, Zoro, and PG Explainer. We observe that GNN Explainer provides relevant explanations and is computationally efficient, where it has a runtime of just 6 seconds. GNN Explainer provides the explanations behind the predictions of GNN. Now, how do we identify the exact reasons behind the failure of the attack through these explanations? We analyze the explanations and observe that the key prediction problem can be mapped to an inverter buffer prediction problem. Consider an example from earlier. Even though the key gates do not have unique mapping with the key value, we observe that the XOR gate with key value of 1 and XNOR key gate with a key value of 0 can be mapped to an inverter. Similarly, XOR with a key value of 0 and XNOR gate with a key value of 1 can be mapped to a buffer. In this way, we observe through this advanced problem modeling, we observe that the key prediction accuracy increases by 1.86 times. The solution too has improved the accuracy of the attack. However, in a realistic scenario, the log designs undergo logic synthesis, that is, a few graph transformations before being sent for physical design. In this scenario, we observe a decrease in the performance of Insight. Now, how do we improve Insight's performance for logic resynthesized design? Through explainer analysis, we observe that the importance scores for the gates around the key gate vary. Thus, we add an attention layer to the GNN that assigns importance scores to different nodes around the key gate while training. Through this approach, we observe that the key prediction accuracy of the resynthesized designs increases by 10%. There could be limited training data set owing to closed source locking technique or limited diversity of training data set. We propose two approaches to tackle this challenge. Firstly, data augmentation. It performs graph transformations on the lock design to increase the training data set. Secondly, semi-supervised learning that utilizes known nodes in the lock design to generate training data set. Data augmentation has increased key prediction accuracy by 1.10 times, and semi-supervised learning has increased key prediction accuracy by 1.29 times. Now let us discuss the overall results of Insight. Insight achieves 2.96 times and 1.86 times higher key prediction accuracy compared to existing ML-based attacks such as COPE and OMLA for all the considered learning resilient locking techniques, including the industry adopted techniques such as TRLL and TRLL+. Now we showcase the efficacy of Insight in recovering the functionality through a real-world image processing application, Gaussian blurring. Given an input as follows, the golden output of Gaussian blurring is as shown over here. The design recovered by OMLA returns an output as follows, which is very different from the golden output. The design recovered by Insight returns an output as follows, which is closer to the golden output. In this way, Insight could recover secret key in practical designs. Please refer to our paper for further results on different hardware architectures such as arithmetic circuits and controller designs and different synthesis settings, and also other practical designs such as crypto cores and processors. Thank you.